In this section, we talk about the relation between the stress and strain. Let us look at the Hooke's law, one-dimensional Hooke's law. It tells us that epsilon 1,1 equal to sigma 1,1 divided by the Young's moduli. Okay, this is the 1D relation. How can we obtain the three-dimensional generalization of this 1D relation? It is easy. Let us look at the expression here. Epsilon 1,1 equal to, we copy this part to this part. Sigma 1,1 divided by the Young's moduli. But because we consider the three-dimensional effect, so we should subtract this stress component by the stress component in the other two directions. Means that sigma 1,1 minus the Poisson ratio times sigma 2,2 plus sigma 3,3. How come we have such kind of modification? Let us explain to you. See, Poisson effect tells us that when you try to pull a one-dimensional bar, pull it longer. If a one-dimensional tensile bar become longer, you pull it in the x1 direction. Then, at the same time, the bar will be contracted, okay, in the x2 and x3 direction. On the other hand, if you apply the force in the x2 and x3 direction, and then you will shortening the bar, right? So, due to the Poisson effect, the elongation effect of the sigma 1,1 should be subtracted to the lateral contraction effect come from the sigma 2,2 and sigma 3,3 term. Okay, so in the one-dimensional relation, low Poisson effect, low lateral contraction effect have been considered. Now, in the three-dimensional relation, we consider both. We consider the tensile elongation effect. We also consider the lateral contraction effect. Okay, so in this way, we can write our three-dimensional stress relation, stress-strain relation easily. And I should mention this. This is a relation which looks quite reasonable, but more important, this relation have been verified many times by actual experiments. Okay, so don't doubt on such kind of generalization. This is correct. Okay, if you accept this, we can write down the similar relations in the x2 and x3 direction easily. Now we had complete the generalization of the normal strain and normal stress relation. For the shear stress relation, shear stress and shear strain relation, low Poisson effect should be considered. So we just take the classical stress-strain relation here. And only one point should remind you. Here, sigma 1,2 should be divided by 2g instead of g. What do you mean? Let me tell you. See, if you draw the relation between the shear stress and shear strain, and you get a line, and then you measure the slope of this line. Listen, be careful. Don't take the slope as the shear moduli. The slope of this line is 2 times of the shear moduli. Okay, so here it is not g. Instead, it is 2g. Okay, or 2 mu. Mu equal to g. They are the same thing. So the slope here is not g, it's 2g. So if you think that the slope of the stress strain relation is the shear moduli, then you are wrong. Understand? The slope of the stress strain relation is not the shear moduli. Okay, it's 2 times of the shear moduli. Okay, this is the tricky point you should pay attention to. Okay, how come such kind of tricky point occurs? Let me tell you. Because we have another definition of the shear strain. See, we mentioned that F 1, 2 is a shear strain here. F 1, 2 equal to 1/2 such and such. We have 1/2 factor here. But in fact, there is another notation of shear strain called delta 1, 2. Delta 1, 2 to equal to this term without 1/2, without the factor of 1/2. You can look at the book. In some book of mechanics of material or elasticity, you can find such kind of symbol, such kind of notation to represent the shear strain. And then there is no factor of 1/2 here. Okay, how come we have 2 systems of the definition of the shear strain? Because in the old day, people get used to use this gamma 1, 2 to represent the shear strain. There's no reason to have a 1/2 factor here. Okay, this one is simpler. We don't need to have a 1/2 factor. Instead, like this. Okay, see, you have a 1/2. If you have a 1/2 factor here, it looks a little bit clumsy, right? Not very neat. So in the old day, people think that the shear strain should be expressed directly in terms of this more concise expression. But after the computer had been developed, numerical computation of mechanics developed very quickly, and very soon people figure out that the definition of shear strain should be modified from gamma 1, 2 to epsilon 1, 2. We have a factor 2 here. Okay, it is a story of mechanics. So I don't want to I don't want to explain too many details here. If you are interested in this little story, you can attend my class of continuum mechanics, because in that class I talk about more philosophy of mechanics instead of the applications. In fact, in this course, elasticity, I concentrate more about the practical application of the mechanics, like mathematical calculation, numerical calculation. So I don't want to pay too many time here, to spend more time here to express this why in numerical computation mechanics we need to have 1/2 here. Okay, but remember, don't get into the trap. This is the trap. Okay. Here, in this 3-dimensional Hooke's law, we compute the strain from the stress. How about we compute the stress from the strain? Means that we get the inverse relation. We have the stress and we compute the strain. But inversely, we can compute the stress from the strain. Like this. This is the inverse relation. Okay, sigma 11 equal to 2 mu times epsilon 11 plus lambda little e. Okay, e equal to epsilon 11 plus epsilon 22 plus epsilon 33. Little e has the physical meaning as the volume change. You can look at the textbook or the internet, and then you can get the volume change expression like this. Okay, this inverse relation can be derived from this relation. Okay, this is a homework. I will assign it to you in the class. Okay, don't worry. You have the chance to practice the mathematical calculations. Okay, so this is the inverse relation. We calculate the stress from the strain. And the shear stress-strain relation is simple. And now we should generalize this 6 equation into one single equation. Okay, use the indicial notation. In terms of indicial notation, this one equation can include all these 6 equations. Let us pay a little bit attention to this. Here in this equation, this is the delta notation. Okay, delta symbol, which just represent the unit matrix. Okay, so delta ij equal to 1 when I equal to j. Delta ij equal to 0 when I not equal to j. This just means that in a unit matrix, the diagonal component should equal 1. The off diagonal component should equal 0. Okay, so this is the feature of the unit matrix. Now, sigma ij equal to 2 mu plus absolute ij and times and plus lambda time E time delta ij. Okay, and little e equal to absolute kk equal to absolute 1 plus absolute 2 absolute 3. Why absolute kk equal to this? I will explain you later. When the index here repeat, it should sum it over 1 to 3. Okay, sum it over from 1 to 3. Okay, I will explain this term later. Now, let me show you from this one single relation, we can get all these 6 equations. If I equal 1, j equal 1, we have sigma 1, 1 here, and then absolute 1, 1 here, and then we have delta 1, 1 here because I will equal 1, j equal 1. Now, delta 1, 1 equal to 1 according here, so this is 1. So this absolute 1, sigma 1, 1 equal to this one, is exactly the same form of this. Okay, so this equation includes this equation. Now, how about the shear component? We put I equal 1, j equal 2. I equal 1, j equal 2, we have sigma 1, 2. 2 mu plus absolute 1, 2. And time and plus lambda need to E delta 1, 2. Right? But delta 1, 2 equals 0, as I mentioned before. So this term drops out. So we get this one. So this one is just this one. So it is easily figure out that this single equation can represent all these 6 equations. Let me talk about more about the indicial notation. We introduced the Einstein notation. It tells us that when repeated indexes appear, it represents the summation. For example, absolute kk are repeating, so it just stands for summation absolute kk from 1 to 3. So like this. But this one can also be replaced by this one. And now according to the Einstein notation, this summation can be dropped out. Okay? And so absolute kk equal to absolute ii. Another example. aij bjk. Now the repeating indexes is j. So we sum it over j from 1 to 3, like this. So just like this. Okay, ai1 b1k, ai2 b2k, ai3 b3k. One more example. When the delta notation, delta ij times uj, we have the summation because j is repeating, j sum it from 1 to 3. So sigma I1 u1 plus sigma I2 u2 plus sigma I free, U free. Okay? And now, if I equal 1, if I equal 1, we have 1, 1, I 1, 1, 2, I 1 free. But 1, 2, and 1, 3 drops out because they are 0. This is equal 1. So equal this, when I equal 1, this expression becomes U1. In the same way, when I equal 2, I equal 2, we have this. And then this one equals 0, this one equals 0, this one equals 1. So we have U2. When I equal 2, same way, I equal 3, this one equal U3. So, when I equal 1, this U1, I equal 2, this equal U2, I equal 3, U equal 3. So this tells us that this term equal to Ui, right? So we get a important relation. Delta Ij times Uj equal Ui. Okay, this is called the contraption law. I will explain this law in more detail. It is very important. Contraption, C-O-N-T-R-A-C-T-R-N. The capitals, the letter C here is missing, so please write C here. C-O-N-T-R-A-C-T-R-O-N, contraption law. Let me give you an example. Delta Ij, Uj. As the example before, we know that when J are repeating, we should replace the Uj by the index here, Ui. So become Ui. This is the old result we have here. Now, if we have delta Aj, Uj, then J is repeating. We replace Uj by Ua. Okay, replace J by A. If delta Jk, Uk, times Jk, times Uk, K is repeating. So we replace Uk by Uj here. Okay, we move J into here. We get Uj. Likewise, delta Ij times Jk. J is repeating. So we replace the J here by I. So J here by I. So Aik. Okay. Here, delta Jk, Km. K is repeating. So we replace the K here by J. Jk. Understand? Km delta Jk. K is repeating. So we replace the K index in the B by J here, by BJM. Similar, we have the example. Delta IA, delta BJ, delta JB, epsilon AB. Let us look at here. A, right? AA. So A is repeating. So we should replace epsilon A by I here. Now B is repeating. So we should replace B by J here. Understand? Similarly, we have delta Ij, delta AB, epsilon Ij. So J is repeating. So we should replace this J by I here to get here. Okay? And epsilon II equal epsilon Kk. Okay? Now we apply this. We will apply this to what? To a new form of the generalized Hooke's law. We write the stress string relation like this: sigma Ij equal to Eij KL, epsilon KL. Here, this is the matrices. This is the matrix of the material constants. Okay, and then the expression of Eij KL is like this. Okay, now I want to show you that this one can be simplified into this one. Okay, this one times this one means that we can, this one times this one means that this one can put it here. So this one put it here, this one put it here, and this one put it here. So sigma ij equal to this one. So sigma ij equal to this one times this one. So we have this one, put it here. And absolute KL, put it here. So this one, put it here. Okay? Now, we can obtain this one from this one. Now let us apply the contraption law. K, index K is repeating. So we should replace this K by I here. I. Right? And then L is repeating. So we should replace this L by J. J. Okay? Similarly, this term, L is repeating, right? So we should replace L by K here. So like this. And look at here. From this one and this one, we get this one again. But this one is just the relation we have talked about before. Yes. Here. Right? We get this old relation again from this more complicated relation. Okay? So this relation actually is equivalent to this relation. Okay? We will make use of such kind of indexal notations of the stretching relation later in the virtual work principle. Okay, so it is very important for you to understand how this computation works. Okay.